Our new unit is going to be about probability and statistics. We're going to do just kind of a basic overview of each just to get you enough to kind of get your feet wet and get a little bit of an idea of what these kinds of things are. And so the first section we're going to talk about is probability and odds. Here's some vocabulary you should memorize, and notice I said memorize. These are things that you need to put on flashcards and start practicing these right away, because these are words that will be used on a regular basis that you will be expected to know the meaning of. So, an outcome is the word we use to describe a possible result of an experiment. I have an example down here at the bottom we'll talk about in just a second. An event is a specific outcome or a collection of outcomes. It's usually what it is that you're looking to have happen. And then the sample space is the collection of all possible outcomes. So here's an example of a scenario and what each thing is. So the example is, when you're rolling a six-sided die, you want to roll an odd number. So kind of using this vocabulary we just talked about, one possible outcome would be to roll a 5. If you roll a die, that is a possible outcome. The other possible outcomes would be to roll a 1, or a 2, or a 3, or a 4, or a 6. Okay? Now, since we want to roll an odd number, the event that we're watching for would be rolling a 1, a 3, or a 5, because those are the outcomes that satisfy that event of rolling an odd number. And then the sample space would be all 6 numbers, 1, 2, 3, 4, 5, 6, because those are all of the possible things that I could roll. So how do we find a sample space? Well, one option is kind of a brute force method, meaning you're just going to start making a list and hope that you get them all. So here's an example. We flip 3 coins. What is the sample space for this scenario? What are the possible outcomes? Well, one example would be that I could get heads, heads, heads on all 3 coins. So another one would be that I could get tails, tails, tails. Or I could get heads, heads, tails. Or heads, tails, tails. Or what else could I get? Heads, tail, heads. Or I think we got most of the things here. And then, we could go on doing this forever. How could you be certain that you got all of them? Well, there's got to be an easier way to do this. Luckily, there is. So, a tree diagram is a really helpful way to do this. So here's an example. You flip a coin and roll a number cube. Now that sounds really dumb to say roll a number cube, but for whatever reason, that's how on the EOC test and on the ACT test and in your textbook, that's how they like to say it. What is a numbered cube? It's a die or dice. Okay, so that's all it is. So you flip a coin and roll a number cube. How many outcomes are in the sample space? List all the possible outcomes. Well, to make sure that we got them all, that brute force method is not usually the best. So here's how we can use a tree diagram to figure this out. The first thing that we're doing is flipping a coin. How many possible outcomes do I have for flipping a coin? I have 2. So I'm going to have 2 branches to start my tree. I could either roll heads or I could roll tails. And then after that step, let's say I roll a heads. Then I'm going to roll a die. What could I possibly get? Well, I could get a 1, a 2, a 3, a 4, a 5, or a 6. Or let's say I rolled a tails first. I still could roll a 1, a 2, a 3, a 4, a 5, or a 6. So now we can kind of follow these branches to figure out the different possibilities. One would be to follow this branch. I could roll a heads and a 1. Or I could roll a heads and a 5. So this whole list is going to give us, this tree is going to give us our whole list. So I could roll heads 1, heads 2, heads 3, heads 4, heads 5, or heads 6. Or I could have gone down the second branch. I could get tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. How many are in my sample space? How many outcomes? There's 12. 12 possible outcomes. We know that because we can count them up. And you could also just go to the end of all your branches and count up how many branches you had at the very bottom altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There was 12 outcomes. The very edge of the tree is going to give you all the different outcomes. So we could go back to that previous example here about, here it is, flipping 3 coins, and I could set up a tree diagram like that. You can do a sideways tree like I did on the previous example, or we could do a vertical tree, either one. So my first coin I flip, again, I have 2 possibilities, heads or tails. The second one has 2 possibilities, heads or tails. And then each one of those, when I roll the third one, I still have 2 possibilities, heads or tails for each one. So if we look at this bottom end of the tree, I had 1, 2, 3, 4, 5, 6, 7, 8 possibilities. Okay? And again, if we went down each of the branches, we'd find them. If I go down this first branch right here, I have heads, heads, heads. Or I could go the next way. I could keep going the same way, but go to the tails instead. So that one would be heads, heads, tails, and so on. You would do that and you'd end up with 8 possible combinations. So a tree diagram is a really helpful way to come up with your sample space. Okay. Here's a third example. I'm not going to work this one out, but I will show you the final answer here. So magically, here is the tree. If we look at the bottom of the tree and we count up how many things there are, you can see I have 6 plus 6 plus 6 plus 6 altogether. There are 24 possible outcomes. You could use that tree then to finish up the question and answer list all of the outcomes. I'm not going to write those out now because that'd be a long video, but you get the idea. So that's how you can figure out the sample space. Now, probability is going to be a number from 0 to 1 that we can use to measure the likelihood, or in other words, the chance that an event will occur. Now, I know you've done probability before, so we can go through this kind of quickly. It can be expressed as a decimal, a fraction, or a percent. The most common is typically as a fraction. If your probability was 0, that means there's absolutely no chance that something could happen. Okay? If your probability was 50, or as a fraction, 1/2, that would mean that you have 50-50, an equal shot of it happening or not happening. If you got to 1, that would mean 100% definitely going to happen, whatever that outcome is. So, any event that you know is going to occur at any given time, it's going to be 100% probability. There are 2 different types of probability. One is theoretical probability. The other one is experimental. They seem kind of similar. The idea of calculating them is the same, but the definition is different. Again, you have to know the difference. These are vocabulary words. So the theoretical probability is based on how many favorable outcomes, meaning how many ways can you get what you want out of all the different possibilities. Another word for that would be the sample space. And some notation here, the way that we can write that is to say P of A. That means the probability of event A. Okay. So here's an example of a theoretical probability problem. You and your friends designed t-shirts with silkscreen emblems, and you're selling the t-shirts to raise money. The table below shows the number of t-shirts you have in each design. A student chooses a t-shirt at random. What's the probability that the student chooses a red t-shirt? So we first need to know two things. The probability is going to come from this. It's going to be the number of ways to choose red over the total number of choices, or the total number of shirts that are available. So if we look at this, we have to think too, how do we read this table? I see that there's gold emblems and silver emblems, and then there's green shirts and red shirts. We're only worried about red shirts, but make sure you notice there's two different choices for red shirts. There's 6 red shirts with a gold emblem, but there's also 6 red shirts with a silver emblem. It doesn't matter which kind of an emblem they choose. We just want to know how many red shirts are possible. So since there's 6 with gold and 6 with silver, that means there's 12 possibilities for a red shirt. Out of how many total shirts, we'd have to add up all 4 of these because that's all the different t-shirts that they have available. So you would do 10 plus 8 plus 6 plus 6, and we get 30. Now, one thing that I want to mention, because some of us forget this sometimes, always reduce. Do not leave a fraction in a form that can be simplified. So can you think of a number that goes into 12 and 30? 6 would be a good one. If I divide 12 by 6, I get 2, and 30 by 6 would be 5. So there's a 2 out of 5 chance that a random drawing would give you a red t-shirt. That is theoretical probability. That's based on every option has equally likely of a chance and the information that we know about it. Now, experimental probability is different. Let me explain to you the difference between the two. In theory, when you roll a dice, you have 6 different possibilities, and each one is equally likely to happen. So there's a 1 in 6 chance of rolling a 1, a 1 in 6 chance of rolling a 2, and so on. Experimental probability is different. We don't go based off of what would be fair or what would be equally likely. You'd base experimental probability based on your own trials. So you would do repeated trials of an experiment. The dice example, maybe I would sit and roll a die 100 times and keep a table. How many times did I roll a 1? How many times did I roll a 2? And so on. However many times I succeeded and got the kind of an answer that I wanted, that's what goes on the top. The total number of trials is what goes on the bottom. So experimental probability is based on data. It's not based on the, in theory, the fair answer would be whatever probability. So this one's kind of weird. Okay, so here's an example. Each section of this spinner has the same area. The spinner was spun 20 times. The table shows the results for which color is the experimental probability of stopping on the color the same as the theoretical probability. Well, the first question is, what's the theoretical probability then? How many spaces is this spinner divided into? It's got 4 different spaces that appear to be equally the same size, and it tells us each section has the same area. So the theoretical probability would be 1 out of 4 for any of the given colors. 1 out of 4 for blue, 1 out of 4 for red, 1 out of 4 for yellow, and 1 out of 4 for green. That's our theoretical probability. But look at the results that we got when we did our experiment. That did not come out to the same number of times for each number like it should in theory. Okay? If we look at this, check how many times did they roll it. Well, they told us they spun the spinner 20 times. If we weren't sure, we could add all of these together, and that comes out to 20 total times. Okay? So what we need to look at is each color. This is a tricky question. This is a very good test question. Make sure you pay attention to the color. or the question. It didn't ask you what's the probability of rolling green or something like that. It said for which of the 4 colors is the experimental probability the same as the theoretical probability. And so we have to calculate that for each. For red, the experimental probability was that we rolled red 5 times out of 20. For green, it was 9 times out of 20. For blue, it was 3 times out of 20. And for yellow, it was also 3 times out of 20. Now, we need one of these that reduces to 1/4. 5 over 20 reduces to 1/4. So the answer would be A, red. The experimental probability, the data results we got, matched the probability that in theory we should have. Okay? Now, the last thing is odds. And a lot of times we hear people use the words probability and odds interchangeably. People say, what are the odds of that happening? And they consider that the same thing as probability. It's actually not. When you hear people talking about odds like in Vegas or at horse races, the odds are 25 to 1 that such and such horse is going to win. That doesn't mean there's a 1 in 25 or a 25 out of 1 probability that it's going to happen. Odds are different. And what odds are is they're a comparison. It's not out of the total like it is for probability. It's the comparison of the number of favorable and unfavorable outcomes when all outcomes are equally as likely. So for example, the odds in favor of something happening, we would say, how many ways can I make that happen versus how many ways can I not make that happen? Think of like a poker hand. Okay, if we wanted to know the odds in favor of getting a straight, we'd say, how many possible ways are there for me to get a straight over how many card hands that are not a straight. So you're not comparing out of all the total possible hands. You're comparing how many ways can you do it versus how many ways can you not do it. Odds against is the same concept, but you'll notice that ratio is just flipped upside down. If we want the odds against something happening, we want to know how many ways can you not get it over how many ways can you get what you want. So let's do a couple last examples here. Okay, here's the same spinner from before. Assuming that all colors are equally likely, find the odds for and the odds against landing on green. So, let's do the odds for. It's for it happening is going to be the good over the bad. How many ways can we land on green? Just one. There's only one green spinner or green section. How many ways could I not get green? Well, I could get red or blue or yellow. There's 3 ways that I could not get green. Do you see how that's different from probability? The probability of landing on green would be 1 out of 4. It's 1 out of 4 choices. But the odds in favor of landing on green is 1 to 3. There's 1 way to get it versus 3 ways to not get it. If I wanted the odds against, it would be the same information. It would just be flipped. There are 3 ways to not get it versus 1 way to get it. So let's say you were betting. Not that I'm advocating that, but that's kind of where these odds are seen the most. Would it make more sense for you to put a bet on landing on green or not landing on green? The safer bet would be to bet against landing on green. It's more likely that you're going to land on something else based on the odds comparison. Okay? So when you see something like the Kentucky Derby and they say, hey, it's a 250 to 1 shot against such and such horse winning. That means there's 250 times more of a chance that that horse is going to lose versus that one possibility that that horse is going to win. That's not a good horse to bet on. So your assignment is page 846, 3 through 16, 19, and 20. This will be due on Monday. You have the rest of the time period to work on this, and that'll be due when I see you when I come back on Monday. Have a great weekend.